Hi everyone, I am Rajitha, working as Assistant Professor of Artificial Intelligence and Data Science Department in SNS College of Technology. Today, we're going to see about local search and optimization problem. So begin with the big idea. And AI, we often deal with problems where we must find the best or optimal solution among many possibilities. Examples, find the fastest route, lowest cost plan, or most efficient schedule. Local search is one of the simplest yet most powerful techniques to do that. Unlike algorithms that explore all possibilities like BFS or DFS, local search looks only around the current position and move step by step towards better solution. The idea is similar to climbing a mountain with fog. You cannot see the whole map, but you move uphill until you cannot go higher. This approach is used widely in optimization, planning, scheduling, and machine learning. Wrap up this slide. Focus on improvement, not exploration of all paths. So what is local search? Start with an initial guess, a random solution. Then look around at neighboring solution, small changes to the current one. Evaluate each neighbor using an evaluation function that tells how good it is. If a neighbor is better, move to it. Repeat this until no better neighbor exists. Example, suppose you want to minimize the distance in a route, you start with any random path and swap two cities. If the distance reduces, keep that changes. This continues until no nearby swap improve the route. Key point, local search does not need the full search tree. It is memory efficient and simple to implement. So key characteristic is current state focus, neighbor exploration, memory efficient. So the algorithm remembers only the current solution, not the whole path. Neighbor explanation is it examine nearby or neighbor solution to see if improvement is possible. Memory efficient is this makes local search ideal for huge or continuous search space where storing all state is impossible. Use a simple analogy like improving your essay by making one small edit at a time instead of rewriting from scratch. Mention that this makes local search suitable for real world optimization like scheduling, network design, and routing. So conclude by reminding that it is a trade-off. We get speed and efficiency, but might miss the perfect global answer. So understanding optimization problem. Define optimization. Finding the best among many possible solutions. Example categories. Shortest path. For example, finding the fastest route from home to college. Lowest cost. Example, minimizing transport or energy cost. Maximum profit, maximizing production, efficiency or return. Explain how AI converts such goals into mathematical model that can be optimized. Mention that best can mean different things: least cost, most accurate, shortest time, or highest efficiency. So end this part by connecting back local search help us reach these best solution effectively. So the objective function is explain the objective function as a mathematical formula that measures how good a solution is. The goal of optimization is to minimize or maximize this function. For example, um, for example, uh, minimization, reduce cost, distance, or errors, and maximization, um, increase profit, accuracy, or throughput. Simple illustration in a delivery system. If total distance 500 kilometer, we want to minimize that, the smaller the better. The algorithm keeps improving until the objective values cannot be improved further. End by emphasizing, everything in optimization depends on how we define and evaluate this function. So a common local search algorithm is hill climbing. Always move to a better neighbor. Fast but can get stuck at a local peak. Analogy, climbing a small hill thinking it is the tallest mountain. Simulated annealing is sometimes accept worse moves to escape local traps. Inspired by inspired by metal cooling, start hot, explorative, then cool, focused. And genetic algorithm works with the population of solution, uses selection, crossover, mutation, just like natural evaluation, keeps variety and explore multiple direction at once. These algorithms trade speed for smarter exploration. And the local optimum problem, define local optimum, a solution better than all nearby ones but not the best overall. Example, climbing a small hill and stopping because all nearby steps go down but a taller mountain exists elsewhere. This is a major limitation of local search. It might get trapped and stop improving. The main challenge is escaping such traps to find the global optimum. Visualize it, a hilly landscape with many peaks. We want the highest one, not a small one. So, escaping local optima, introduce strategies to overcome the local trap problem. Random restart. Try different starting points. Some runs may reach the global best. Simulated annealing allow occasional downhill moves early onto escape traps. Population diversity, use multiple candidate solutions like in genetic algorithm to explore more areas. Real world analogy, if one road is blocked, start again from another route. And the conclude is escaping local optima makes local search more powerful and flexible. And the real world application is scheduling and planning. Allocating resource efficiently. If example, course timetable, project task, assignments, factory jobs, networking design, optimizing route in transport or communication system, resource optimization, managing energy stock or investment portfolios. Real example, Google Maps uses optimization to compute shortest route. Emphasize local search is practical and applicable across many domains. So the key takeaways is efficient and practical, works well with large complex real world problems. Trade-off, it is faster but does not guarantee the perfect answer. Wide applicability, useful in AI, robotics, logistic and data science. End by summarizing, local search teaches as that sometimes good enough solution found quickly or better than perfect once found too late. This is the mind map for a local search optimization problem. Thank you.